and it's just starting. Okay, thank you.
So this is the P4 OVS update. So we open sourced this in September, as I just mentioned last year, and I just want to tell everybody what we have been doing since then, and what is expected by Q2 June end. So how do I go to the next? So this is the agenda for today. I will start with the feature update, what features we've been working on and what are expected by June, followed by the architecture update that we've been discussing with Red Hat. And also then I will go into a deep dive for the control plane packet design for P4 IPDK, and then end with the summary. So the feature update, we had some requests to add the tap port support into the open source OVS, and we've been able to upstream that. Along with that, we have added the action selector support. And you would have seen a lot of activity going on the IPDK container that is using P4 OVS. But those changes are for another day. I will stick to the P4 OVS update today specifically. For targeted for Q2 is hot plug for chemo. For those of you who are following the updates would have seen a patch for this, a code review for this generated also on P4 OVS. So this is to add the VHost ports into an already running VM. So we went and re-architected it a little bit, and we have some things to move to P4 DPTK target because the code because some of the code belongs there. So once that is done, we will be pushing this as well into the open source. Then we've been talking about Linux networking.p4 file. We've been working that. We are probably 90% done for now. And that supports L2 forwarding, VXLAN, ECMP, routing, control and exception packet flow, where your control packets go to the OVS and your exception packets go to your SDN controller. And then we have also added connection tracking and mirroring capabilities onto that P4. So this P4 file, we will be open sourcing it in around May-June timeframe. And to hook up this P4 file into the kernel control plane, we have that code in progress. We call it the kernel control plane. It listens to the configurations from the kernel and uses switchlink and SCI to program it into your end targets. So this is in progress as well. We are first making it work with L2 forwarding and VXLAN. And as soon as this is done, maybe we can come back and give a demo on it and also raise the code for review. Then we have port adds for control tap ports with vHost ports. I will go over this in my section 3 so everybody understands what we're doing here and can provide their inputs. We have statistics, port counters, and port config dump, and flow counters and flow dump. That is an implementation. We are also working on integration of TDI. So TDI is the abstracted interface for the end targets. So once this TDI integration is done into Stratum or Stratum code or the P4 OVS code, we will not have to switch the target linkage in P4 OVS. We'll just be calling the TDI APIs, and that is supposed to link with the end target. So you can switch the end target in and out pretty easily. Then we have PTF and UTF in works. We have enabled the base PTF and enabled the simple L3 pipeline that we open sourced in September, the use case. And and more use cases are in progress, and we'll have some of the use cases upstreamed by the end of June. And as well, UTF, we are planning to implement UTF using GTest. And yeah, we'll implement some of the base use cases, but we'll have the framework ready in a couple of months. We are also planning to enable Jenkins CI/CD on the P4 OVS open source repo. So after that, our contributions can directly go into DPDK instead of going through the internal and then creating a patch for open source. I will also talk about the split architecture modules that is in the architecture update that we have been working on and discussing with Red Hat. So once this is done, you'll see other modules like K-Control P4D and Infra P4D. These names are subject to change, but for now we have named it this way. And another OVS fork with much smaller changes, a better Stratum integration, and a P4 and M client library for any controller to talk to P4 OVS. So this is all targeted for June, and we will be sending out patches as soon as we are ready with each of these features. And talking about split architecture, my next section is on that. Does anyone have any questions on the slide?
So you'll end up
Okay.
posting that P4 file on the website, and we can potentially have its own review session for that file.
Oh yes, yes.
Okay.
Yeah.
So many different
Maybe we
ways
can
to
bring
write.
it here. Yeah, maybe we can bring it here as an update as well.
Okay, yeah. It's just you can write ECMP 100 different ways in P4. So we just have to find some way to get agreement on what's the right way to write it, so that the compiler doesn't have to handle all 100 different variations. So we'll have
Right.
to think through what's the right review process for that.
Okay. Yeah, so we have started with hash table and action selector, but yeah, we'll bring it in the review, and then it can be discussed in an open forum. So moving on to the next one. So this is the current architecture that we follow right now. You see a lot of components in OVS, P4 OVS right now. So we have the P4 runtime controller and open config controllers hooked onto OVS itself. And then we have the kernel control plane also working in, which is listening to your netlink and switch link and programming your SI interfaces and your P4 IPDK target. Everything is the TDI is linked into your P4 proto, which is a parallel of your OF proto. And then we have provided two CLIs, the P4 kettle, and we call it GNMI CLI right now. We were working on this, and this is a very big patch to upstream to OVS, and also we wanted to cleanly structure it and have well-defined roles for each of these components. So we are moving to a split architecture, as we call it. So this is what we are moving on to. So this basically has an advantage that it will segregate the control and data planes in different blocks. And then the upstream for OVS will be minimal. We did talk to Red Hat about this design, and they seem to be agreeing with this one and have suggested suggested to add the OVS DB client over here. And yeah, so I'll talk about that. So so Infra P4D is going to be our main P4 runtime and open config server. This is driven from Stratum. We picked up a lot of Stratum code in P4 OVS. And you'll see the same code going in Infra P4D right now, but we are actively working with Stratum to get a library defined and include that library in here. So this interface becomes very clean by the time we have Infra P4D. We are also working on TDI integration. So now instead of the P4D target, we are going to interface with the TDI in this library. So this is the module that will link to your P4D PDK target and will be a data plane plus P4 runtime and open config control. The server will have the P4 runtime and open config server capability. Now we can connect different controllers to this. One is the SDN controller, as we were doing it before. And so we have the P4 runtime and OpenConfig client running on the SDN controller, and this can send the messages. There is this red line, which is exception packets, which can go from this P4 IPDK target. If there's a miss on any table, which P4 does not understand, it can go to the SDN controller to get processed from here. Then we have K-control P4D. This is the kernel control plane that I showed in the last slide, which was integrated with P4 OVS. Now we are pulling it out and calling it the kernel control P4D daemon. So this will have your Linux networking pipeline, which will support your kernel functions. And this will listen to your netlink and SI API. So earlier we were calling an API into the P4 run into the TDI from here, and now we are going to call it a controller and basically program it via the P4 runtime messages into your infra P4D. So this becomes your one control plane. The SDN controller is another control plane. Then we have the CLIs that we have already implemented, the OVS P4 Kettle and OVS and the GNMI CLI that work with OVS right now. So we pulled it out. This can be used to program again using your P4 runtime client capabilities. So this is one block that you can manually set some rules and set pipeline into the infra P4D and your target backend. Then we can have more control planes here, like storage, strong swan, which don't need your control, K-control, P4D or OVS, and can directly use this infra P4D module. So for OVS, because it's P4 OVS, we have to make it work with OVS. So for OVS now, the thing that we need from OVS is when the control R packets go up and OVS populates the L2 tables, we want these L2 tables to be propagated onto your Linux networking P4 because that contains your L2 pipeline. So these tables, so there's this interface that we'll implement in OVS, probably using TCP sockets, and then this can program the L2 tables, and you can have a P4 runtime client running into your infra P4D to program those tables into your target backend. We also have a control packet processing in OVS. So these control packets are actually any kind of packets which you want to send for OVS OpenFlow processing. You can send it via this red line. And I'm going to talk about this line in my section 3 when I explain this control plane architecture. So this OVSDB client here listens to your OVSDB server in OVS and all the configurations that come into OVS. These configurations can be translated to the P4 runtime and TTI calls, and your DPDK can be programmed from here. Any questions, comments on this slide? Okay.
One thing we have to do on IPDK is to standardize the exception paths. Is to have a way to define how the exception packets will come in and out of different applications. I think the OVS, this P4 OVS or the OVS, the patches for P4, they only use kernel net devs for exception packets, right?
Right.
Okay.
So yeah, I'll go over that how we can send packets to OVS, because OVS works with kernel netdev and P4DPTK works with user space netdev. So I'll be talking about that in section 3, and these are exception packets which these are packet in packet outs basically, which you really want to go to the SDN controller, but you can very well have any packet more than ARP going into OVS and have software handle the exceptions.
I see. So so you do have both kinds. You have kernel exceptions in OVS, and then you might have an SDN controller exception that goes through user space.
Right.
Okay. So we should standardize this because Sonic does things in pretty much the same way. So we should pick it so that specify it so it's easier if someone wants to write another application or wants to add an application to this picture here, that they know like which netdevs to use and things like that. So I'll take that as an AR so that I think we should spend some special time on it. It is currently, very specific to OVS, but we should try to standardize it so that not everyone has to like redo it every time.
Okay. Any more comments or questions? So as I mentioned in the feature update, we a couple of team members are working on this, and we are planning to open source this K control P4D and infra P4D in IPDK as well. And we'll have a different fork of OVS because now it will have much smaller changes to upstream. And then this can be picked up and worked upon by anyone. Moving on to the next section. So I'll be jumping onto the details of this control packet processing in the next section. So, oh, sorry. So this is just a reiteration of what I said and what each of the modules contain. So OVS contains your L2 bridging interface and 2K control P4D and any open flow rules that are needed. Infra P4D will have the P4 runtime and open config server functionality. It integrates with TDI. It interfaces with the target backend via TDI. And it contains the OVS DB client as well for port reads and any configuration reads from OVS. Then we have K-Control P4D, which is the owner of Linux networking P4 and drives the kernel configurations. This is integrated. There is an integrated P4 runtime client API to interface with infra P4D here to program this pipeline and to add the rules into this pipeline. Then we have this is what is explained in the third point. And then we have interface to OVS to get the L2 table entries that are configured in the inner bridge. Then we have CLIs. We have infra P4 kettle and infra OP kettle, which is the P4 runtime and open config clients that we currently call OVS P4 kettle and Genome CLI. These will be the names of these will change. And any other control plane, storage, strong swan, microservices, firewalls can be integrated, can use the integrated P4 runtime client functionality, which will be open sourced and can talk to the infra P4D here. So this is the control packet flow design. So here, I know a lot of blocks here, but I'll explain each of them. So on the left side here, we have OVS. As you can see, this is the OVS vSwitch bridge. This is the kernel module where you can see your vxlan configured in the kernel bridge and talking to OVS. OVS will have some internal ports on the inner bridge, which will represent your VM connections. On the right side, we have a couple of VMs. We have open sourced this code of adding the VirtIO port into the VM and attach it to the P4 IPDK target. So I hope everybody knows this concept. And so this basically represents that. And your middle section here is basically your infra P4D, which is your P4 runtime config monitoring service, and which interfaces your TDI and your TDI target library. This is an expansion of your P4 IPDK target, which explains your pipelines. So the lower one is your underlay pipeline, underlay networking pipeline, as we are calling it, which is the Linux networking pipeline, which will have your L2 forwarding and VXLAN and routing and ECMP, all those functionalities. And then we have the Open vSwitch pipeline, which is the overlay networking pipeline, which is basically connected to your VMs here and also has any virtual capabilities that are needed in addition to your networking pipeline. So, so here we added the VHost ports, which are talking to your VMs here, which are connected to your VMs. So here we are running with one data plane, which is P4 IPDK, and your OVS, as Dan mentioned before, we bring up OVS using the Open vSwitch kernel module here. So now we need to add different interfaces to this OVS. So OVS can listen to some specific packets that are coming from your P4 pipeline, and your P4 IPDK target basically becomes your main packet processing pipeline. So for that, for these VHost ports and every port that we add onto your P4 IPDK target, we have planned to have a pair port, which is pair tap port that we're calling. So this This pair tap port is basically a one-on-one mapping right now from your from any of the ports that are connected to your P4DPDK target. So for here, this VHost port, and from here I'll go to the next slide, I think. Yeah. So here you can see this VHost port is connected to has a pairing with your tap port, which is your tap 0. So your VM1 representer on OVS is the tap 0. Then your VHost port for VM2 is connects to your tap1 net device. Your ring port, so ring ports are basically used to send packets between these two pipelines. So this is a stacked or a layered architecture where you can have different functionalities in different P4s. And if you want to send packets between your P4s, you can use these ring ports. So your ring port has a representation as well in the tap2 net dev. So your physical ports, port 0, port 1, here which terminate on your Linux networking pipeline, which are listening to the outside packets. I have a tap port representation here. So this representation is terminating in kernel for your routing or ECMP packets that need to be processed by your kernel. So both of these ports will have a pairing with a tap port that terminates in the kernel. For your Open vSwitch pipeline, the VM representers are actually added onto the OVS bridge here. So when you send a packet on tab 0, your OVS is actually able to process this packet. So when your packet comes into tab 3, your kernel stack is going to process this packet. So this is the architecture. So suppose we have an ARP packet that's coming in from VM1, ARP request coming in from VM1. We can have a rule in this pipeline that if a packet is coming into this VHost port and is an ARP request packet, which P4 pipeline does not process, you can send it out to your tap port, which is the tab 0 net dev, into your OVS to get it processed. So in OVS, you have the L2 switch working, which will broadcast this ARP packet onto all the other ports. Excuse me. Onto all the other ports. So your ARP request is going to go to your tap 1 and tap 2 and other interfaces that are connected to the OVS. So once it is sent on tap 1, here again, you can have a P4 rule saying if you see an ARP request on the tap port, send it to your pair port. So it again goes to your VM2. Your VM2 is what you want to reach. So this will send you, this will send an ARP response into P4DPDK. So this response is again an ARP packet. It's supposed to be processed by OVS. You send it out via tap 1 here onto the OVS bridge. OVS bridge is going to add this ARP response and the MAC address corresponding to the IP into your L2 table and program the K-control plane, which will program your networking pipeline. And also, it is going to send a response back onto your tab 0 net dev, which is going to your VM1. So now your VM1 has your ARP response and your packets can flow directly from VM1 to VM2 from here on. So this is just an example of ARP. You can use it for any packet, as I said, if you want some specific packets to be processed by your OpenFlow pipeline, you can just send it to your overlay networking pipeline and into the tap port, the corresponding port that you're receiving the packet from. For your routing and ECMP, when the packet comes in from the network, these packets go into your tap 4 net dev and tap 3 net dev and get processed by your kernel. Your kernel bridge will contain your vxlan and also a lag on top of it. Lag under it basically. So these two ports can be lagged as well, and then you can create tap ports onto that into your kernel bridge. VXLAN sys 4879 is what OVS creates for sending out VXLAN packets into these VXLAN tap devices. So this is how the control packet flow is going to work with the P4DPDK target and the P4 OVS. With your hardware pipelines, it's a little bit different because you have your drivers running in, and they can create the tab devices specifically needed for the kernel edition, the kernel tab device, the kernel net devs basically, which can be added onto your OVS directly. So you don't need these tab interfaces over there. But for P4DPTK, this is the first cut that we are following, and this has a disadvantage of having too many net devs. If we need too many of these VMs, like thousands of VMs will need thousands of net devs, but then we can come back and use some metadata or make modifications here in this pipeline to address that issue. Any questions on this?
I was wondering regarding this P4 DPTK target, is there any possibility that this can be offloaded to the hardware, or is it like more like using eBPF for getting the packets from the net devices in Linux kernel?
Yeah, so we are not offloading anything from the P4DPTK onto the target. If you want to offload onto the target, you can just use your the backend API that we'll use is for your target, just like the P4DPTK target API. You'll have your hardware API, which will be linked into your TTI, and you can just offload onto that. So that will be like a proactive pipeline. In that case, when your control packets come up, they will come up using some driver and into your kernel netdev or your user space netdev, and that can be added onto your OVS bridge, and your OVS can listen onto it and take an action. So this is, we have a proactive implementation here. So the expectation is that you will have most of the flows configured, most of the rules configured into your hardware or your P4DPTK target before you start passing the packets. The reactive, there is no reactive flow add here. But there is a reactive mechanism of getting the packets onto OVS, and then OVS itself will forward these packets from the host itself or from your hardware.
Okay, thanks.
Any more questions? Okay, moving on to the next slide. So we have the VHost. These slides summarize what I just explained. So we have two P4DPTK pipelines that are used for supporting end-to-end functionality. We have the Linux networking pipeline that is driven by kcontrol P4D, which is the underlay networking. And then we have the Open vSwitch or container pipeline that could be the overlay pipeline, which will also contain information on your VM pair ports. Then these pipelines are connected using the ring ports, open config utility, which is GNMI client right now. This is used for doing the port-to-port pair port mapping and configuration. We have additional tab devices created for each regular pipeline port. We have pair port tab devices used for sending control packets to OVS. We have underlay tab devices that are used as regular netdevs in Linux networking stack to process routing, FRR, ECMP packets. And the overlay tab devices are assigned to Open vSwitch and are used for L2 bridging. Then this is the GNMI CLI that we've implemented internally. We'll soon bring it to the open source. This is your VHost port, and you can go ahead and auto configure your tab port, the control tab port that will be used. And they should populate your P4 tables and your P4 pipeline with this information. And you can have a control block saying if it's an ARP package, you hit this table and you actually go to the OVS. So the summary, I talked about the changes for P4 for the tab port addition and action selector, which are already upstreamed. Then we have big feature rich patches coming up by June, which will have, so we'll send it via multiple code reviews. We are not going to push out another big patch. So everybody has a chance to review these feature-wise patches. These will come as and when we implement the features. So this is going to contain the end-to-end working of Linux networking and control plane flow to OVS and kernel enabled. We have port management, flow management, and the statistics implemented. We'll also have TDI integrated. We're planning to have the split architecture components, open source and IPDK. The PTF and UTF baseline code added, and then Jenkins CI/CD enabled on open source by the end of Q2. and I hope we get done with all this. So, so this is it for today. Thank you for listening, and it's open for questions if anybody has any, or if anyone wants to add anything from the team or Dan, please go ahead.
Oh, you know me.
That's why I
Thank you.
called you.
This was really good. I really appreciate taking the time and going through all the different steps of what we're working on now, and also happy to take up any of these topics on Slack or email or in our any sort of existing communication paths that we have. And trying to get this more out in the open. Red Hat's been giving good feedback about using the OVS dev email mailing list. So we'll try to be more communicative, and of course we're also moving a lot of this development directly into open source. With that last bullet at the bottom. So, hoping to make it easier to get involved and contribute as we make these changes to make the whole ball of changes a little bit more manageable within the system.
Okay.
Cool. Thank
So,
you.
Catherine, can we turn off the recording?